All right, so we're now recording, and so just to repeat for the recording is we're not going to get our kits for about another week or so. So the first lab is going to be pure just simulation and analysis with some exposure to FDTD. So hopefully it looks like about 90% of you have done FDTD before, so you've got some good experience with that. And there'll be a couple of you who might be a little in the dark on that, so there'll be a tutorial posted on just what it's doing and how it works, and you should be able to at least kind of tentatively make sense of it. You won't have to know much about the simulation itself, but you will have to be able to tweak it to do a few certain changes for the model. All right, so that being said, I guess that's our only major announcement. We've got our TA as well. She's very helpful, and we've tentatively planned out about 5 labs for the class. So at this point, you should all be caught up on lectures, and we're just here to kind of play around and do some theory and answer questions and do practice problems. So we can open the floor to all your questions, and if you have specific problems you're struggling with, we'll go over them. And any just, I guess, theoretical stuff. Hopefully you all got a chance to watch the lectures, and my goal was to just really give you intuition on what's happening within transmission lines, right? A lot of these textbooks, they just sort of jump in and give you the theory and the math, but a quick overview question is, no, physically, what's happening in terms of the little charges wiggling around and bouncing into things? That's a very important intuition to have before you start digging into the mathematics. Oh, we have a hand raise. That's a feature. I did not know Zoom did that. So Chad, what do you got for me?
So I had a question about the quiz. It says that it's due like, I think next Monday. Would
Yes.
the quiz, would those be best to do after we've done the entire week, kind of like over the weekend? Or when would it be best to kind of do those quizzes?
All the material in the quiz should end Friday. So you should be able to get started on some of it right now, at least to do the first one if you did the reading, and you've got your 3300 information there. And then Friday we'll do some basic transmission line stuff where just the forward and reverse propagating waves. So how do you convert from voltage to current and calculate power and that kind of thing. And that's it. And so then you'll have the whole weekend plus a Monday to ask questions and get that done. So that's the idea.
Cool. Thank you.
Is the lab going to start this week or next week?
Oh, thank you. Next week we'll have our first lab.
Okay.
And that's a good question. When are the labs specifically? I think there's lab on Wednesday and then Friday, I believe. Can you guys tell me when your times are for your labs? I think one was like 7:30 to 11:30, or was it? Tell me the times for your labs again. So we got Friday, 7:30 to 10:30. Okay. Stuff is all online. And is there a Wednesday, 3 to 6? PM. So that's gonna suck for you guys on Friday. You have 3 hours of lab and then another hour with me. So I think that's it. There's just the 2 lab sessions, right? Because there should be like 8 of you per lab. Am I getting that right? No one's correcting me, so that's it. So that's the idea. Starting next week, this will be your first lab. So I'm hoping to have a lab kind of assignment up by then. I got a rough idea of what I want you to do, and I put together the code that kind of does it. I just need to figure out some basic instructions. And Berardi left a kind of example lab report of what he's looking for in terms of how these reports should be formatted. So you'll have just kind of a basic introduction where you'll do an overview, then you have maybe like a theory section, then your results and a discussion kind of flow to it. So I told the TA, it's kind of, we'll figure out, I think she said she wants to get a couple days in advance where she'll work on it and then figure out a rubric. And I'm going to kind of just let her do most of the grading on that. But if you think she's being unfair or unreasonable, you can always just appeal back to me. these should mostly be kind of like pass-fail things, right? You'll do the theory, you'll get a nice prediction of what should happen. And if it's working, then great, you just write it up. And as long as it's clear that you did the work and you more or less understood what was happening and convey that information to the grader, then you should be just fine. So I think I uploaded that example, but I'll put a link to that as well. So yeah, starting next Wednesday, we'll have our first lab. So the idea is you should have about 3 hours with the TA to just do it, where we'll show you the simulations and you can screen share and do that kind of fun stuff. And then the next session is you'll have a 3 hour block where you basically take that time to write up your results. Right? So that was the reasoning that Berardi gave to me for how he did it. And so we're just taking that system and going with that. All right, any other big conceptual questions? Because we can just do homework, or I can just show you fun simulations, or if you just feel like you're on top of everything, you can just go ahead and leave maybe. I was thinking eventually I'll have like a quiz or two from time to time, just to kind of, as a way of promoting attendance to the sessions. But otherwise we can just start going through homework problems. So what do you guys want? It's kind of in your hands now. Presumably you've watched the lectures and you've got a nice background on all the material, and it's in your hands what we do now. So if there are no questions, I'll just do kind of an overview of the quiz. So I'm not seeing any hands raising.
Just wondering, so are we always supposed to finish all the study, including lecture and book reading, on Tuesday, like before Wednesday? Then both Wednesday and Friday would just be working on homework kind of sort of time.
So the material, lecture 2 is just up to Wednesday. Lecture 3 will be up to Friday. So technically I'm not assuming you've watched all the way out to lecture 3 yet. If you did, good job. But really we're gonna do just kind of like one lecture at a time. We don't wanna open up too much of a fire hose of information.
What do you mean by lecture 2? Because from what I see, there's only week 1, and it's just like a group of videos packed together.
Let's see. So let's put the module there. So there's week 1.
Oh, number 3. Okay.
So week 1, learning materials. So it says video lectures. It should say 2A, 2B, 2C. That was all the we're up to today. Then there's a 3A and a 3B. I think there's a 3C I may have recorded and not uploaded yet. I'll have to make sure about that. But that would be all the you'll need to go through by Friday. Does that make sense? Because really,
yes, it does. Sorry, yeah, I thought we need to finish 2 and 3.
No.
Yeah, before today. Okay, great.
So each lecture, I'm hoping, will just be a single day. Although I'm kind of wondering if that makes sense. If we're going to have week 1, I should probably say lecture 1. No, because we'll have multiple lectures per day and multiple days per week.
I think it's good. This format is perfect. So
Okay.
Lecture 2, no matter it's 2A, 2B, or 2C, it's the Monday one. Then yeah, I think it makes sense. Thanks.
Okay, yeah, that's fine then.
Right. I have a question about concerning the video lectures that you've placed on the week 1 materials. I noticed that there is a lot of conceptual derivation of the telegrapher's equations, the characteristic equations that are how we come up with characteristic impedance. So those videos outline the derivation that I assume Maxwell went through. Maxwell, and I'm not sure if Hertz did this, but how they came up with the idea that there is a characteristic impedance that defines the transmission line. What I want to know is, I suppose, how does this translate into a problem? Are we expected to perform the derivations ourselves from scratch? Is that one of the
so my expectation
questions?
is when you watch the video, you'll at least follow along and make sure the reasoning makes sense. And I may or may not throw a little bit of derivation problems at you from time to time in a quiz, but usually to be pretty straightforward stuff. Like one of the quiz questions I asked, I believe at the end, was just showing that the wave equation for the solution to the voltage actually satisfies the wave equation. So that'll be like 4 lines that you just take a picture and submit. But like, no, you don't have to like, are you asking like, do you need to rederive all of this from scratch or?
Well, I mean, presumably what is presented in lecture is the material that each student is expected to learn, correct?
Mm-hmm.
So what I see in lecture, I imagine will, you know, be on the exam, be in the homework. But when I look at the homework, that's not the case. The homework has information that is solely in the book or has to be kind of, I don't know, pieced together by the student. Does that make sense? And I worry that about the piecing together part, I suppose. Piecing together equations, tying together concepts. The lecture seems to not address that. It does address derivation very thoroughly. And I do see the line of rationale where one concept flows through the other. But for instance, this first equation, even this first problem I'm looking at, uniform plane waves, is kind of a review of old concepts, which I remember vaguely. I don't recall that when I was in 3300 that I tied together magnetic field and electric field and calculating from an amplitude another amplitude of the magnetic field given a frequency. I don't recall a problem like that. I don't recall that exercise. So I'm kind of at a bit of a struggle. I don't know if the rest of the students are experiencing this. Am I the only one?
Well, do you want to ask the class, or because I don't know if you want everyone to answer that or not, or you make it more?
I would.
I assume that's why our instructor is doing a reverse class, so we can know the derivation of the equations before class, and during class time we can have like more hands-on practices. That's my assumption. If that is the case, I think it perfectly makes sense, unless there's like a different planning.
Or just answer Chad. Yes, the quiz is the homework assignment. It's just the assignment section in Canvas, you can't create fill in the blank problems, but in the quiz you can. So the quiz problem sets are your homeworks. So sorry, could you repeat your question there, Yoshi?
That was not a question. That was
just. Or sorry, what your comment was?
Oh, my comment was just, I think Ben was worrying if we're going to learn a lot of derivation of equations, while that is not highly associated with like exams or homeworks questions. So I would just say my assumption is we are learning the derivation.
Oh, sorry, you cut out there for a sec. But
of equations before class, things like that is more similar to homework questions or exams, or maybe they're just homework questions, you know, like, so that was just my assumption.
Have you attempted the homework, Yo-Yo?
I took a look. I haven't.
I would recommend looking at the homework because it seems to me that, I mean, I do understand that homework is meant to test the student, test your critical thinking skill, tie together concepts on your own. I just worry that there is not enough, perhaps enough material to guide the thought process to solve these questions.
Well, for what it's worth, the first set, I just kind of assumed you've taken 3300 and you read chapter 1, and a lot of that material is there. So I didn't do any lecturing on that at all. That was
Okay.
just a giant presumption on me. After that, if you get to the rest of them, it's all going to be based on just book and lecture.
Okay.
So think of this section, that first problem set is more dusting off some of the cobwebs to help get a feel of what you know and what you don't know. Because part of the point of these sessions now is for you to kind of ask the questions and say, I don't quite remember this from 3300. Can we review that a little bit? But for what it's worth, the uniform plane wave stuff is not going to be the central focus of this class or this section. It's mostly just, it's there in chapter 1, and I just want to, that information is buried in your head somewhere, presumably, if you took 3300. Even if it was a year or two ago, it should have been in there. And if you read the chapter and kind of pull out your book from last time, you should be able to make sense of it. And if you're struggling on that, just ask questions and we'll go through it together. And we'll even point to the sections in the book where the answers are. But these particular questions on plane waves are not really going to be on exam 1. Exam 1 is all about transmission lines and stuff. So kind of keep that in mind. So I guess withhold some of that judgment until you get to the transmission line sections, and then go through those problems, and we'll see how you feel. And if you still feel like there's some disconnect, we can go from there. Does that help?
Yes, it is very helpful. I don't mean to criticize your curriculum. It's just I'm kind of worried of my own self-interest, I suppose.
Okay.
Am I going to survive this class? That's the question that's the question on my mind.
So yeah, the way my style is, as far as the lectures go, I'm going to be heavily focused on the derivation specifically and conceptually, like, what does this stuff mean? What are some ways to visualize it? Like all day yesterday, I put together this PowerPoint slideshow on just what on earth is a Smith chart all about, and what are all these goofy lines and markings? Because I remember going through being extremely confused, even seeing the derivations and reading it again in the textbook and not really being clear on like what all that gobbledygook is about. So I'm trying to focus a lot on conceptually, this is what is happening, so that when you finally see the mathematics, you can tie it to a picture. And then the homework sessions are really just applying those lectures and not so much testing your knowledge per se, but I try to think of more in practicing the application of that knowledge there. But that's actually a good point. Is in the lectures, I probably could stand to do like a practice problem or two in the lectures maybe. But that was kind of what I was envisioning these sessions for. Like, and now that you've got kind of the questions down and here's these homeworks, let's do some practice problems together. So in fact, that's a great segue. So we can whip out our second camera over here. So the first question is just asking things like, here is a plane wave. Like that. So you imagine the electric field propagating along the z-axis. So I already kind of answered a bunch of this, but I think half of you didn't quite join the session yet. So if your E field is polarized this way along the y direction, so you imagine the right-hand rule. So the thumb points in the direction of propagation, your fingers point in the direction of the electric field, and then you curl into the direction of the magnetic field. So I want to see some hands on those cameras, right? So the question would just be, what is this direction coming out of the page given y and z? So I drew this little axis here. So if I have y and z, you'll notice it goes into the negative x direction. So that is one of the answers now, is that's the direction of your magnetic field. So that's a little hat there like that. Okay, so the idea now is you imagine your electric field will look something like this. We do this in the time domain. You have E naught cosine of omega t minus beta z. Or if that's a wave number, sometimes we use k for that as well. Those tend to be interchangeable in this context. So then the question would be, what is the magnetic field right here? So there's a number of ways to go about it. One way is just skip to the end, but you can actually just prove this from Maxwell's equations directly, where you would have something like the following, where the curl of E is equal to the negative time rate of change of magnetic field. Or if we're in phasor domain, we can rewrite this a bit. We don't have to do this all out in time domain. We could write this, say, as E of Z is just E naught. That's a y hat. We put y hat e to the minus j beta z like that. So there's the phasor equivalent of this expression over here. So then Faraday's law in this context would become the curl of E is equal to minus j omega v, which implies negative 1 over j omega times the curl of E is equal to V. So the only real question is, how would I calculate that thing in terms of this guy? So you can actually just write this out, minus 1 over j omega. You would say del cross E naught e to the minus j beta z times y hat equals v like that. And the curl is kind of difficult. So notice we're doing kind of first principles. If you skip ahead in the reading, there's little shortcuts you can do for this. But you notice this curl, whatever direction it is, we don't really care. It's just going to be a derivative with respect to distance. So if you work out the full 3 dimensions of this curl, you'll get an answer. But the shortcut would just say that this del cross here, that curl, is just going to be a derivative with respect to z. Because all the other derivatives have to be 0. Because if we're only changing in z, we can kind of wave our hands a bit and say we don't have to worry about that. So if you really want to be heroic, you can write out all 3 components of this and figure out how it relates to this. Or you can just kind of say, well, the only change is in z, so that's the only possible derivative I'm going to care about. And the right-hand rule already told me which direction it's going to be. So you can shortcut a bit. But the long story short is you'll get 1 over j omega. There'll be an x hat, because we're in the negative x hat direction. And E naught times the partial with respect to z of e to the minus j beta z. So the derivative of this guy just means I'll get the j beta up front. So we'll have, let's see if we can write this out. We'll have a j beta over j omega E naught e to the minus j. You can see that? Beta z is equal to my magnetic field. So there's a lot of wacky stuff happening here. And just remind ourselves there's a negative x hat there. I'm not going to really bother writing it because all we care about is the magnitude right now. So the j's go away. You'll notice that's, if I take the magnitude of all this, that little guy goes away. Sorry. I just did some scribbling there. So let's write that again. I just skipped like 3 steps real fast. So we have, oops, try to get my head out of the way. There's a beta over omega E naught e to the minus j beta z is the magnitude of the B field there. If I take the magnitude of all of that. So the magnitude of this whole thing means that complex exponential is going to disappear. What you'll have is just the magnitude of that. So this is in the book where it says eta was basically omega mu over k, because beta is omega over k as well. Sorry, these are betas. Sorry, I'm mixing up my betas and my k's. So basically, at the end of the day, you get this little scale factor here, which turns into the eta. Let's see if we can find that in the book here. Let's see, beta over omega E naught, where beta is equal to, sorry, I got a little ahead of myself. What's going on? What's your question?
Which page of the book is that?
Or you're saying
Right here
omega
on page 17 talks about some of this stuff.
Okay, thanks.
Right, I'm doing some of this out of memory, and I got about 90% of the way, and then I crashed into my own mental block here. So you see how it has the partial with respect to z, only they have the h here instead of the b, so that's where that mu term is coming from. So you follow some of that, and you can do that derivation. I wasn't really expecting to have to like go through that derivation. I'm just kind of running through it very quickly. The point is, it's right here in the book where they do exactly what I've just done, where you have some electric field, right? And you plug in Maxwell's law, Faraday's laws, and you can do all that stuff to get the H field out here.
So are we solving the quiz problem 1? Is this?
Yep.
Okay, cool, thanks.
So if you go through all of this, what you'll find is the magnitude of the H field is simply the magnitude of the E field divided by this eta naught factor.
So you're saying that omega equals 1 by saying beta equals omega over beta.
No, that I put in the wrong value there, sorry. So beta should be, how do they do that here? They have the lambda. Oh, they didn't do it quite in terms of beta, did they? As I believe the way it works is the wave number is omega over c, the speed of light. That's right. Sorry, I got my symbols confused there. So that is where you get some of that stuff. So what you'll get then, let's see if I can do this from memory.
To clarify, you meant that beta is the wave number?
Yes.
Which is, I think, n in the book, right?
They call it
I'm not
n?
certain. I'm not certain.
No, sorry, they call it k here.
K.
So for some reason in electromagnetics, they like to use k for wave number. And then
Okay.
you get to transmission line theory, they start using beta. So I apologize if my head is a little scrambled. I just spent the last several days doing nothing but transmission lines. I'm using beta here. In the book, it's K. They're kind of synonymous though when you're doing these wave equations. So I'm sorry if that was confusing, but you basically get the square root of mu naught epsilon naught times omega here. So that's when you can calculate the magnetic field, but then you also have to remember that magnetic field is u naught times h, like that. So when you solve for h, you get some terms dividing into each other, and then the upshot is this expression here. Is all we care about. That's where the eta comes from. So I wasn't expecting to do this whole derivation kind of from scratch. The whole point is if you just kind of read here, that's your answer at the end of the day. And so it just came right out of Faraday's law. So I was trying to say, if you get really motivated, you can go through that kind of derivation right out of Faraday's law to figure this stuff out. And a bunch of coefficients start banging into each other. So we'll just kind of skip to the end. But all I really wanted you to remember is the magnitude of the H field is magnitude of the E field divided by eta naught. So that's the answer for the H field. And then the magnitude of the B field would just be mu naught times the H field. This is for free space. Obviously, if you're in a magnetic material, you'd add the little mu sub r there. But that's just one in this case. So that's really all I wanted to refresh in your memories there. So if you read through that particular chapter, that should have refreshed a lot of that. And if you took 3300, you hopefully did some of those same derivations as well. Sorry, that was a little rough trying to do that from memory. So that's essentially, let's see, your first question. So yeah, calculate the magnitude of the magnetic field. That's this guy here. And then the auxiliary magnetic field is this one over here. Those are your first two homework questions. Problem 3 then is the direction, which we found was just the right-hand rule. So that's problem 3. And of course, this was 100 volts per meter. So you can do the calculations on that guy pretty well. Let's see, question 4.
Oh, and mu naught is like 377.
Say again? Oh, this guy here.
Uh-huh.
Yeah. So eta sub 0 is the square root of mu naught over epsilon naught, which is approximately really close to 377 ohms. So that's right there in the book as well. Right here. Right there on page 17. It should have all your answers.
Right, sorry, I feel like it has been too long ago. So mu naught and epsilon naught, they both have like fixed value, right?
Yep, that is correct. So let's see if I can do this from memory. Epsilon naught is 8.854 or something, something. So this goes out to like 9 decimal places times 10 to the minus 12. It has units of farads per meter. So that is called the permittivity of free space. And that is just a physical constant of the universe we happen to live in. So you can take that as just an empirically given number. And then the way Maxwell's equations are set up is mu naught is equal to 4 pi times 10 to the minus 7 henries per meter. So these are good numbers to try and memorize if you can. It'll be in your book. It probably is like an inside cover. We have all the constants somewhere. Most textbooks like to do that. No, they don't actually. Oh, interesting. Maybe it's something in the back. Aha. Oh, so here's some fun reminders of all those vector operators if you really want to remember how curl and everything works. So there's gradient, divergence, and curl. All that fun stuff. We're going to deal with some of the Laplacians at some point. Oh, they don't have the physical constants in here. That's kind of disappointing. So it's probably in the chapter 1 somewhere where they actually give you those values. Do they not? Here we are. There's mu naught and epsilon naught right there. So that's rounded down a bit. There's actually 9 more digits if you really want to get accurate. But for most engineering purposes, you can cut it off right there.
Which page is that?
That is page 7. So these are important values to kind of write down somewhere and have access to. For stuff like this, I'll often write, oh, maybe it's right here. Sorry, I had a piece of paper. Right? Do they have it here? Oh, they don't, he doesn't even have it on the inside cover. So probably for this sort of thing, I'll often just like write it on the inside cover of my book or something so that it's just there whenever I need it. So I'd put like mu naught equals and epsilon naught equals there. So you just always have it right there if you ever forget. Those are numbers that you will have to recall a lot. Because that's just literally the universe we live in. Okay, so those are problems 1, 2, and 3. Question 4 is, how fast is the wave propagating? So obviously an electromagnetic wave propagating in free space propagates at the speed of light. So you should be able to pull that out. But a good relationship to remember is that the phase velocity for a wave in free space is 1 divided by the square root of mu naught times epsilon naught, which just so happens to be the speed of light. So that's kind of a gimme question. It's literally a wave of light propagating in space. How fast is it going? Well, the speed of light. Oh, we got a question. What is the 3300 book? I got my copy over here. Let's see. I don't have my copy. There it is. So this is the book for ULAB, Fundamentals of Applied Electromagnetics. So if you took 3300, this is the book you should have used. And yeah, so this guy is actually clever enough to put some of those constants on the inside cover. So hopefully you didn't sell this book back, because this is another one of those really great books to hang on to. So let's look at question number 5. Uniform plane wave, same idea, calculate the wave number. So this idea of a wave number is really important. That makes a good little segue into a review. Remember, we have this idea of frequency, there is wavelength, then you have period, and then you have this idea of wave number in a sense. And how do they kind of relate to each other? Then you also have this angular frequency over here. And then of course there's a propagation velocity. There's some analogies to this stuff that's worth understanding. So remember, you have this notion of frequency, and then there is period. Okay, so if I have a wave in time, imagine this is my time axis here, and this is some wave going along. The distance from here to here is called the period. We're all kind of familiar with that notion, right? And then the frequency was 1 over that. So by analogy, let's suppose I have a wave. You can see that. I'm going to draw a little bit better wave here. And that just kind of goes on. So now imagine it's a snapshot of a wave. Like I'm watching waves on the ocean and I take a picture of it. So instead of time, this is now distance. So you have this notion of here to here is called a wavelength, right? So you have this notion that period and wavelength kind of share this analogy where if this is in time, this is in distance. Then you have frequency, well, I guess by analogy, you'd say frequency is sort of like 1 over the wavelength. So the inverse of period is frequency. So the inverse of wavelength is this thing. I don't know if there's quite a name for that. But we also have this omega being 2 pi times f. So that would correspond to 2 pi over the lambda. And that is called the wave number. So you can think of it as like a spatial period, spatial frequency. So K is spatial frequency. Like that. So if this would be, the period here, would you think of it in terms of seconds per cycle, or lambda would be meters per cycle. Frequency is cycles per second. So this spatial frequency here would be cycles per meter. And then this omega here has radians per second, because it's 2 times pi times that. And so K now has radians per meter. So I remember really kind of struggling to make all those connections. Nobody ever spelled that out for me. That's the idea of wave number in a nutshell. You can think of it as an angular spatial frequency. But yeah, so intuitively, that's the name that should have been used, but we call it wave. So that's a great kind of mental connection that I just remember it took years and years before anybody like drew that connection for me, kind of showed all this stuff side by side. So just omega and K are kind of the same thing. This is in time domain, that's kind of spatial domain. Okay, any questions on that? I'm just kind of trying to fill in a lot of these intuitive conceptual gaps that may or may not exist before we get into really the meat of transmission line theory. So then, of course, yeah, calculate the wave number, calculate the wavelength. A lot of that stuff should all be very familiar if you've done anything wave related. And then let's see. So then finally the phase difference, right? So you have this wave like so. We're going along. This is space here. So this is my electric field, say, in space. I'm looking at a snapshot. And we have my field here at 0, and then I move over here like 20 centimeters, say. Is that what we say, 20 centimeters? Yeah. So the question is, how much does my wave shift in phase through that distance? So that idea is you have this e to the minus j kz. So that kz represents phase shift over distance. So you can just say delta phi is K times delta Z, like that. So that'll tell you how much phase is. So if I go, for example, let's say delta Z is 1 wavelength. So I let delta Z equal lambda. And that implies K is 2 pi over lambda. So then delta B, therefore, would be 2 pi over lambda times lambda becomes 2 pi. So you see how there's 2 pi radians over the space of 1 wavelength. So from here to here is 2 pi radians of phase shift. So I'm hoping this is all stuff you kind of already are familiar with. But again, there's going to be a lot of dust and cobwebs on these concepts. So I'm hoping to just kind of shake some of that loose by going through all these practice problems. These are terms that are going to come up again and again and again as we go. So that's
Initially,
yeah.
oh, sorry.
Yeah.
Just commenting, that was very helpful. Initially, I was looking at question 7 and thinking, hey, it's a uniform plane wave, and I kind of, for some reason, tunnel visioned into the idea that uniform plane waves don't have a phase shift. I don't know, a phase difference between the two waves. Yeah, I tunnel visioned on the wrong thing. So.
Oh, that's good. So that's why we're here, is just go. And so again, think of these as practice problems to jar some stuff loose. So as far as the first exam goes, I'm not going to really focus on this plane wave stuff. But a lot of these ideas of phase and the difference between phase, wave number, wavelength, these are things that are going to be relevant when we do transmission lines, because there are going to be more wave equations with stuff bouncing back and forth. And there's going to be all sorts of wonderful phase things cropping up as we go through that. So finally, question 8. So this one you may or may not have really focused on in 3300, but it's the idea of power flow. What is power? In fact, that's a good question. Did they ever go through that in 3300? This idea of power density? Because you imagine an aperture. It's like this. So here is like something like this. And there's a bunch of light coming in from the bottom. Okay, so let's see. You can consider this like a piece of metal like this. So it's covered up and there's just an aperture in it. I'm shining a flashlight in from the bottom. So a bunch of energy comes in from the bottom and spits out the top, like that. So let's say this aperture here is exactly 1 square meter. Okay, and let's say up here, I just measure the actual power that's piercing through that little hole. How much energy would I capture through that? I might capture, let's say I get E is exactly 1 watt. Okay, so what you would say though is that all that power was distributed through this area here, that aperture. So this introduces the idea of a power density, which we usually denote with S. And it would be power divided by area, like that. So I would have a power density of 1 watt per square meter in this aperture here. So the derivation for that from electromagnetic field theory is kind of intense, but the upshot is it's a pretty straightforward question, or quick, straightforward calculation, where the time averaged power flow in an electromagnetic wave is 1/2 times the real part of E cross, that's a cross product, H conjugate, like that. So that's the generic expression for the flow of power. So that is generally true for just any arbitrary bunch of waves crisscrossing. But for a plane wave, it actually comes out to a very simple equation. The magnitude of E, I think it's times the magnitude of H, like that. Which you'll remember, the magnitude of H we solved a minute ago. Where's that other guy? Was this here. So if I just substitute that in, you'll get 1/2 times the magnitude of E squared divided by eta. So that is how you calculate the power density in an electromagnetic plane wave. So given some electric field intensity propagating through space, there is actually this real flow of energy in that wave. So that, I believe, is in the book. So let's see if we can find the page where that's at. So I also just skimmed this. So let's see, plane waves. He gets through here. Does he actually talk about power flow? I'm pretty sure, I remember seeing that somewhere. Spin depth, general plane wave solutions. Energy and power, here we go. So he does this horrible derivation of it, which I'm not at all expecting you to really follow. But the answer at the end of the day is pretty straightforward. So he talks about, that's kind of the general, there's where you get this E cross H, which eventually, if you really are dedicated, you should finally get to, wow, he doesn't, maybe I gave you a question that wasn't quite in the book. Well, he sort of talks, because there's a hint of it right here with the E over eta. Is it anywhere in here? Yeah, that's the power flow, E times H constant. So you can do a time average of that. I may have just given you a question thinking it was in the book, but you didn't actually have the simple answer anywhere. Well, there's your answer then. I apologize about that if that threw you for a loop. Yeah, because he sort of hints at it here. He never just comes out and says it. So I'm pretty sure at the very least it's in here. But that's the solution you need to use there. So don't worry, all my other questions are going to be based off of lectures. I was just kind of assuming this was in the chapter and in here. So write that down and use that for the solution there. And I believe, yeah, that's all the review on electromagnetic plane wave stuff. And then eventually, then we start getting into transmission line bits. And I think, yeah, if you should not have done any of the telegrapher equation stuff, right? You did the lumped element model here. And then we did the telegrapher equations. And that's kind of where we stopped. So the rest of the quiz material is just on the wave solutions to the telegrapher equation. So are there any questions or comments there? We're almost out of time here. We got about 5 minutes left. If you have anything else you want to discuss.
I just have a question about the recorded video. So you would send the record video link to us like kind of right after?
Yes, so that's a good question. Would it make more sense to just sort of upload it to Canvas? I'll probably just stick it in kind of like the media gallery for this stuff, so it'll be there somewhere. Yeah, when we're done here, I'll find a spot on Canvas to upload this bit.
Another thing I was thinking that it seems like you recorded from your like James Nagel.
Oh, that's a good point. I need to pin my video of the, yeah, that I didn't think about it. So there we go. So I need to pin my video to the camera here, don't I? So here is what we're talking about here. And is the host the only one who can record? None of you can just record a session? Is that accurate? None of you have just a simple recording option anywhere?
I just tried, it won't let me.
Unless we have a password from you.
A password? Isn't just the
right?
to get in?
So we need like record permission from the meeting host.
Yeah. How would I give it then?
I don't know.
Slides, yeah, whenever I do like a PowerPoint slideshow, that I can upload. I think I already uploaded the first bit of slides. I just need to activate the files section, I think. So yeah, I uploaded them, but the files section right now is disabled. So if I enable that for the students, you'll be able to see some of the lecture slides. So just for the sake of the recording, this is the equation you'll need here for the plane wave stuff with power flow. And then there was this kind of analogy between period, wavelength, frequency, spatial frequency, angular frequency, and wave number, that idea there. And there was some of the other bits we drew. This isn't the most compelling stuff. You'll need definitely these physical constants memorized. And here's the relationships between field amplitudes. So if I have the electric field, I can calculate the H field. And if I have the H field, I can then calculate the B field. Stuff. All right.
Once we,
Yeah?
sorry, I don't know if somebody was going to speak first.
No, go ahead.
Okay. Once we do finish this, this problem set, is there reading for next week to kind of get an early head start on that?
Oh, yeah. So let's look ahead here. So the first bit, you should have gotten all the way up to the lumped element model in your reading. And that was, I believe the lecture just kind of went ahead and got all the way to the telegrapher equations here. Where are the telegraphers? Here. So these are the telegrapher. I like to say telegrapher, just flows better. So this was derived in the lecture, and this is the phasor domain bit. I think this is about as far as the lecture's got. So for Friday, it's still section 2.1. So we're going to go over all this stuff in the lectures, all the way out to here. And then I believe this section 2.2, we're not going to quite do because that's where they derive some of the stuff using like pure electromagnetic considerations. So this is a good chapter, just kind of read 2.2, but we're not really going to be tested on this particular material. Yeah, so they derive like L prime and C prime just from the geometry using electric fields and magnetic fields. So this is good to kind of peruse, just to know that there's a connection between the actual electric and magnetic fields here and how to solve them, but we're not really going to focus on that stuff. You should have done a lot of that in 3300. I don't want to get too bogged down. So then for next week's stuff, I believe, so yeah, power flow, you'll kind of need to understand a bit. That's going to be an important idea. So then next week, we're just going to kind of keep going. 2.3, we're going to do the lossless terminations. So reflection coefficient derivations, that kind of stuff. And I think this is about as far as I got in recorded stuff. But we're going to keep going into all the way into the Smith chart. We're going to keep doing that. So keep reading there. And then we're going to, some of this slotted line stuff we're not going to worry too much about. And then the quarter wave transformer, I believe, is what we'll get to by Friday. So just kind of keep on reading through in your book. And then, yeah, so then I believe this is going to be the end of next week. The week after is when we'll start it. So just keep on reading through. So by next Friday, we'll be to about here. All right?
All right, so 2.3 to 2.7-ish.
Yep.
Or 2.6-ish. Okay, thank you.
Yep. If you really want to be a hero and get ahead on that, then I applaud you.
I'll definitely be looking forward to the videos that you present on Canvas because I mean, the book is pretty math heavy. The way that you explain the telegrapher's equations, for instance, is a little bit more intuitive rather than looking at the math derivations.
Mm-hmm. And I think that's probably a little intentional because well, this book is kind of written under the assumption that you've already sort of taken one of these classes. So some of that initial material is going to be a little, what's the word, quick and dirty, whirlwindy, I guess, is that the word? So that's something I really wanted to focus on, was kind of reminding you guys about the fundamental intuition of what's really going on here. Because yeah, just because you took the class on it doesn't mean it's all still perfectly recollected in your heads. Especially the Smith chart. I'm going to really try hard to make that thing intuitive, because I remember struggling so hard with what on earth is all of that scribbly nonsense on a Smith chart trying to tell me. So I've got a whole lecture of just what is the intuition of that we're going to do. So that's going to be pretty much all of Wednesday. Right? So there you go. So that's kind of a quick introduction. And I'm sorry this is going to be a little bit of a rough cut because I'm still getting the workflow going here. Like, for example, I really should have been recording this instead of me. So I apologize about that. But I'll make sure to do that next time. And any other little suggestions like that are very helpful. So I guess that's it. So have fun with your next set of lectures, and your problems will get a little bit more transmission line heavy for the next set after you do these next lectures. But it's just going to be, here's a transmission line, here's a wave, find its impedance, find the inductance, find the wave velocity again, and all that fun stuff. Yeah, question?
Just want to verify, you said you're gonna post those papers that you just like wrote down on Canvas, right, later?
Oh, you mean this, my hand scratch, chicken scratch here?
Yes.
I could, I just don't feel good about what I did today, but if you really want to see this, I could.
Yeah, I mean, if you want to reorganize it, it's totally fine. If not, it's great too.
I mean, because I was just crisscrossing everything. I promise I'll do better as time goes on. This is my first real attempt at some of this stuff.
Yeah, I mean, if you want to reorganize it, then put it on Canvas. I think it'd be like really great. But if you don't, I think it'd be good for us to at least just have, you know, the information of everything.
Well, I like the idea of just recording this. So if you go back, you can download the recording and you can just see it all as it goes. That to me makes the most sense. Although I will try a little harder to be a little neater as time goes on. I'm still kind of getting the hang of this.
Yeah, because I think 2/3 of the video was not recording the handwriting.
Okay, then yeah, that's
A lot of that was recording you, so I think the first 2 pages might be missed.
might be missed.
Okay, I guess that would be good too. Yeah, thanks.
Okay. Okay, let's call that a day, and I'll try to get my workflow a little better, more improved by next time. So, see you guys later.
All right. Thank you. Appreciate it.
Thank you.
Thanks.